Okay, as usual, we had a disagreement because I did something really stupid, but here it is correctly. Just as I said before, this is 1/4 of 2 pi, which is pi over 2. This is half of pi, which is pi, not pi over 2, right? 2 pi over 2. Okay, well, anyhow, we can cut all these angles in half. Let's draw a line through here, 45 degrees, and another line through here at 45 degrees. Half of pi over 2 is pi over 4. Now, you get these angles quickly and easily without having to think too much. If this is pi over 4, then this is what? It's 2 pi over 4, isn't it? Of course, that reduces to pi over 2. But now, if this is pi over 4 and this is 2 pi over 4, I bet you can tell me what this is. Can you hold up some fingers to give me a hint what you think? Yeah, it's 3 pi over 4. And this is 4 pi over 4, which of course reduces to pi, and 5 pi over 4, and 6 pi over 4, which equals this, and 7 pi over 4, and 8 pi over 4, which is 2 pi, and then we get a 9 pi over 4, 10 pi, and reduce. Okay? So that's really easy. Have you ever seen this picture? Used it? Familiar? Okay? At least familiar to one of you. One of the most important pictures you're going to run into ever. Okay? Totally fundamental and easy. So if you haven't seen it before, you have now, and it's easy. Okay. Now, there are 3 other angles that we can do, and we can express exactly as multiples of pi. I mean, we express a lot of angles exactly as multiples of pi. But the geometric connection's clear here. Okay, if we draw a line here and a line here, I'm not doing a real good job of this. This is 1/3 of the right angle, this is 2/3 of the right angle, and this is the right angle, okay? Now, how many of these do you need for the whole 2 pi? Well, you need 3 of them here, right? 1, 2, 3. So you need 4 times 3, because there are 4 quadrants. You need 12 of them. So it's 2 pi over 12. And of course, that reduces to pi over 6. And then this is 2 pi over 6, which reduces to pi over 3. And this is 3 pi over 6, which is equal to 2 pi over 4. Which is equal to pi over 2. Okay? Then we got the same thing over here. And you just go around the circle. You got 4 pi over 6, which equals 2 pi over 3. 5 pi over 6, which doesn't reduce. 6 pi over 6. 7 pi over 6. What comes next? Well, it's 8 pi over 6 equals 2 pi over 3. 4 pi over 3. Okay, just like most days. Okay, 6 pi over 4, or 9 pi over 6, which equals this, which equals this, but of course this equals this. Okay, and then 10 pi over 6, which is 5 pi over 3, 11 pi over 6, and 12 pi over 6, which of course is 2 pi. I'll write that down. There's your picture. Okay. Now, this picture is very handy because you can use it to plot polar equations. And unfortunately, we've used up over half the time. We haven't even gotten to cylindrical spherical coordinates. We're going to have to do it anyway. But we want to lay this foundation, because if you don't have this, you don't have anything. Okay? So what would we do if R was equal to, let's say, 2 sine theta? Well, I don't have time to make a table and explain the calculations. If theta equals 0, you should know the sine function. If theta equals 0, the sine theta is 0. Okay? So we have the origin. Okay? And that's the point. Well, I'll label it in a minute. Okay. Sine of pi over 6 is like the sine of 30 degrees, one of your special angles. The sine is 1/2. So we have this point, which I will label. That's 1/2 pi over 6. At pi over 2, the sine is 1. So it's going to be twice this. That's going to put it out here. So that's 1 pi over 2. Now, if you want to do pi over 4, that's fine. You could do square root of 2 over 2, which is about 0.707. Okay? And again, you just got to know that. You got to know the sine of 60 degrees is about square root of 3 over 2. Square root of 3 is 1.732, so that's about 0.87. Okay? If you don't know that about the sine, then you're not equipped to really understand what goes on at these angles. Okay? Now, back in the good old days when I was in school, everybody with an IQ over 40 knew the square root of 2 and the square root of 3 to 4 significant figures. Okay? I'm exaggerating. Everybody with an IQ over 20. At 40, you don't even understand numbers, I don't think. So, okay, well, anyhow, there you have it, right? So you can see what's going on here. Is this going to be a spiral? Well, you're going to come out to 0.707 here, so I'll just put that lightly, and 0.87, which is getting pretty close to 1 here. So you've got an arc that looks like this. And now you go through these angles, and you can verify what happens to the sine. Well, by the time you get to pi over 6, you're down to 1/2 again, and then you're down to 0, and you're going to go through these values as well. What's that look like? Looks like kind of a lopsided circle, but it should be a perfect circle. Okay? And you can prove it's a circle. Oh, you know, this is supposed to be R equals 2 sine theta, because I put the 2 there. I forgot about the 2, so I'm just doing R equals sine theta. If it's 2, then you're going to be twice as far out, and your circle's going to have twice the radius, okay? So this is R equals sine theta. Center of the circle is here. If you put it in rectangular coordinates, this is a point 0, 1/2, right? You can prove then that the distance from this center out to any of these points is always the same, just using some trig identity. Okay? It looks plausible, but then maybe I am trying to fake you out and I just drew it so it would look plausible. Well, of course, you know I'm not doing that, but you need to verify that using a little trigonometry. I recommend that as an exercise. I wouldn't do it, but that's the kind of thing I would do if we were spending a week on a chapter on parametric equations and so forth. And you're going to be very glad by the end of the semester that we didn't, okay? That's on you. Of course, if you've got questions, let me know. Yeah. I'll answer them outside of class or whatever. Can't take class time on it. No more class time on that preliminary chapter, okay? So you should at least work through the part on polar coordinates. Okay? It's easy. It's very easy. Now, a couple of equations that are really obvious. If this is r and this is theta, then if you want the x and y coordinates, x is r cosine theta, y is r sine theta. This goes back to the circular definition of the trigonometric functions, which I really hope you got to, instead of just right-angle trigonometry. Circular definition of the functions in terms of the unit circle, which is represented by all this. Since you haven't all seen this, you really need this. You're going to need it in physics too. You're going to need it to understand the pendulum, as I said. Okay. And it's not hard. Okay? So you have a conversion between polar coordinates and rectangular coordinates. Okay? Now in a minute we're going to go on to cylindrical and spherical coordinates. Okay? Cylindrical is easy if you understand polar coordinates. Okay? Just polar coordinates in the XY plane and the Z coordinate brings you up out of the XY plane. Okay? Or down below. Spherical coordinates is a little weirder, but if you understand this, it's not too hard to understand what's going on there. Okay, anyhow, you have conversion from rectangular to polar. Pythagorean theorem, here's x, here's y, here's your right triangle, so there's r, the hypotenuse. That one's really straightforward. I'm sure you understand that instantly. Theta, I think I might have written something like this out. I know I've written it out, I don't remember where or when. Okay? Everything's still kind of a jumble of confusion with my 3 other courses, which are so similar I can't keep them straight. Okay, this one is unique and I've taught it 10,000 times. 2 of the other 3 I've designed and I'm being taught for the first time. I'm real confused. Which class is doing what? Okay, anyhow, theta is the inverse tangent of y over x. Okay, so again, I don't remember where or when I wrote the inverse tangent. It was either this class or physics. Wouldn't have been the other one. I think you've seen that. If not, then I hallucinated it or something, but there it is. Okay? And that's your conversion from rectangular to polar. So I can convert this equation, okay, to this. It's a little tricky. You know, you get r, which means you got the square root of x squared plus y squared equals the sine of the inverse tangent of y over x. And we won't worry yet about the 180 thing. That kind of works out. How do you do the sine of the inverse tangent of y over x? You draw a picture of the inverse tangent of y over x. Here's y, here's x. This angle is the inverse tangent of y over x. What's the sine of this angle? Well, the sine is the opposite side over the opposite. Okay? So this has got to be the square root of x squared plus y squared. Okay? So, x squared plus y squared equals y. Okay, you get x squared plus y squared minus y. You complete the square on y squared minus y. You get y equals quantity 1/2 squared. And you have to add 1/2, 1/4 to that. And you get 1/4. You get then x squared plus y minus 1/2 squared equals 1/2 squared. And by translation, all the stuff you learn about transformations, we talked, that came up in physics, I think, yesterday. So by something that I'm going to be covering in pre-calculus today, early in the semester, there's your equation. So you need to reconcile that. Because that's pre-calculus algebra, okay? And analytic geometry. Again, you need to understand that, and you got to be able to complete the square on this equation. So if you complete the square, see how you get this. And then if you replace y by y minus 1/2, that moves the origin to the point 0.1/2. Okay, now we've got less than a half hour to cover cylindrical and spherical coordinates. I'll dispose of cylindrical coordinates rather quickly. Because it's easy to visualize cylindrical coordinates. So here's x, here's y, here's z. Well, start a new video here. That one ran on for 17 minutes.